Hi, everybody. Welcome to Chapter 7, Part 1. This is probability. So, Chapter 7 is about the basic idea of probability. Now, let me tell you why this is an important chapter. We're actually not going to spend a ton of time doing just probability stuff in this class, but probability is the bedrock of how we generally do hypothesis testing. So, when we're looking at a hypothesis, the outcome is going to be based on a probability of getting that particular score, that number, that statistic, when it might not be true, right? When there's no relationship between a couple variables. So what we're going to get to, and you'll see this more in further chapters, but what we're getting to is the idea is, let's say that I think that wearing glasses makes you more attractive, right? Well, whenever I do my study, I'm going to get a number, okay? And that number is going to say, hey, this is the relationship between those two, between glasses and being attractive. So it'll be a numerical representation of the relationship between wearing glasses and being attractive. But there's always a probability that I could have gotten that number when wearing glasses has nothing to do with your attractiveness. Probability is the basis of this idea of hypothesis. So that's why we're going through basic probability to begin with, so that we can understand it in an application later on. So we're going to talk mainly in the first video about discrete probability. We'll go through the addition rule and the multiplication rule. And then we'll get to ideas of the continuous probability, the binomial, and the normal curve and the normal approximation coming up in the second video for this particular chapter. So let's go ahead and start. Is gambling a good investment strategy? Now, I hope you said false if you're thinking about gambling in terms of going to a casino and gambling. Now, a lot of people would say that, using the stock market is also gambling. You're just gambling with different probabilities. Whenever you go to a casino, the casino knows that you might win, but it also knows that there's an overall probability that they are going to win. So, of course, some people win sometimes, but there's an overall probability that the casino is going to win at any given moment. So what we're going to talk about today is ways of calculating the probability of certain occurrences happening and how to understand those things. So let's go ahead and start with this basic idea. A priori versus a posteriori probabilities. So a priori means prior, right? Before, prior. Posteriori means after. So prior probability, priori, a posteriori, after, meaning after the event happens. So what this is really talking about is if you have a probability of something happening, what is it versus what it might be otherwise. So let's say that let's start because we're going to use decks of cards as an example. So, oh, these aren't going to show for you. Let me show the back and see if it'll work. There you go. Okay, so these are my son's Mario cards. All right, let's see if they'll show you the faces. Probably not because they're the same as the background. Oh, that's too bad. Anyway, oh, there we go. You can see some of them. Okay, good. So these are a standard deck of cards. In a standard deck of cards, there are 52 cards. 52 cards. And 13 of them are hearts, 13 of them are spades, 13 of them are diamonds, and 13 of them are clubs. All right? Each one of those suits, whether that's diamonds, spades, clubs, etc., has 3 face cards: Jack, Queen, and King. All right? So, what does this mean? Well, what is the probability of me getting a red card? If I take this deck of cards, right? I spread them out, I randomly pick one card out. What is the probability that the suit is going to be red? That means it's going to be either a heart or it's going to be a diamond. What is the probability of that happening? An a priori probability would say, all right, well, let's think about what is the number of events classified as A. So A in this case is getting a red card. All right. So what are the events that are classified as A? Okay, well, if we know that in this deck, half of them are red cards, that is 26 out of the 52, right? So 26, we have 26 red cards in the deck. The total number of cards is 52. So 26 divided by 52 would be the probability of me picking this one and getting red. Now, you can't see that because of what's going on. Oh, there you can see it. It is red. Okay? So what was the probability of that happening? A posteriori means that all I do is we actually do it and see, did I get a red one? It's the number of times it occurs and the total number of occurrences. But in this case, we're saying, all right, let's say that instead of just doing it once, let's do it 1,000 times. A posteriori just says, okay, let's just do it 1,000 times. And then you just see how many times red occurs. So that one's red, there's one. Do it again, put it back in. That one is black, right? Do it again. That one is red. So we got, 2 reds, 2 blacks, and you just keep doing that over and over and over again for 1,000 times. Then you say, all right, I did this 1,000 times, and I got 500 reds and 500 black. That's a posteriori. You go in there and you just do it over and over and over and over and over again. You say, well, the probability of getting a red card was 500 divided by 1,000. So a posteriori, the number of times A occurred, the number of times red occurred, divided by the number of total occurrences. So the number of times you pulled out a red divided by the number of total times you pulled a card out. So in that case, it'd be 500 out of 1,000. A posteriori, you actually have to do it over and over and over again. A priori, you know what the probability is before it happens. So you don't have to do this 1,000 times. That would take a long, long time. You won't have to do it 1,000 times. Instead, what you do is you say, well, I know that if half the cards are red, then the probability of me getting half of them to be red over 1,000 trials is going to be half. It's going to be 0.5. We like a priori probabilities because we can know what they are before us taking all the time to do 1,000 card pulls. We don't have to do that every single time. We can calculate it beforehand, prior, a priori. So everything that we do in this chapter has to do with a priori probability. That is, calculating the chance of this happening. Now, does it happen in real life? Or would it actually happen if you did 1,000 pulls? Well, if you did 1,000 pulls, you might get 501 reds compared to 499 blacks, something like that. So we might not be exactly accurate a posteriori, but we know overall what it should be. In the same way that the casino knows a priori the probability of them winning, a posteriori might be that you win a few times. Okay? That's the difference in this mentality and the math that we're going to do. So the math that we're going to do is all a priori math. So in a standard deck of cards, what's the probability that you're going to get a red card? It's 0.50. Probabilities are from zero, a zero probability, to a 1. A 1 means 100% chance of it happening. So 0 to 1, those are the probability ranges that we're going to use. Those translate into percents if you want them to. So 0.50 is the same as a 50% chance that something would happen. But in general, when I'm asking about probabilities, I want the actual decimal number. So if I ask you, what is the probability you'll get a red card? The correct answer would be 0.50, right? 0.50 would be the probability. Great. All right, when we talk about a priori math and a priori probabilities, we need to talk about the addition rule and the multiplication rule. So let's start with the addition rule. The addition rule is not just what is the probability of me getting a red card. It is the probability if I only one event, right? So in this case, we're just going to do one card pull, right? One pull. The question is, what is the probability of this being a red or a club, for example? So the probability of A or B. So the P, that means probability. A would be the first event. So that would be pulling a red card. And then the probability of B would be pulling a club card. But then we have to subtract the probability of A and B. That is, what would be the probability of me pulling out a red card and a club card, that this was both red and a club at the same time. Now, in that instance, we wouldn't worry about it because you cannot have a red card and a club card. Red cards are either hearts or diamonds, and club cards are black. So this cannot be both a red card and a club card. It's got to be one or the other. So mutually exclusive means that these events are one or the other. So for example, being red and being a club, you can't be both. You can't be both. However, being red or being a face card, those are not mutually exclusive. You can be a red card that is also a face card. So those are not mutually exclusive. Red and face card are not mutually exclusive. Red and club, those are mutually exclusive. And so the way you do this is you look up the probability of the first thing and then the probability of the second thing, and you subtract the probability of both happening at the same time. Exhaustive means, does this show all the possible outcomes, right? So for example, being red, if it's exhaustive, then the probability of it happening is true. So exhaustive would be something like, is it red or black, right? The probability of being red plus the probability of being black. And that's exhaustive. It's going to be both. It's going to be both of those things. All right, so let's think about this. We're going to talk about this and do some examples. So let's do the first example that we just talked about. What is the probability of me pulling a red card or a face card? Let's do that, red card or face card. So what is the probability of pulling a red card? The probability of pulling a red card, we've already determined that, is 0.5, right? 0.50. Okay. Now we need to add the probability of pulling a face card. Okay. There are 12 total face cards. 12 total face cards that are in the deck. So 3 for hearts, 3 for diamonds, 3 for clubs, 3 for spades. Those are the 12 different face cards. And 12 divided by 52, I'm doing this on my calculator over here, is 0.23. So the probability of me pulling a red card or a face card is the probability of pulling a red card, 0.5, plus the probability of pulling a face card, 0.23. But then I got to subtract the probability of pulling both a red card and a face card. So I need, what would be the probability of me getting the jack, queen, or king of hearts and the jack, queen, and king of diamonds? And so then we got to subtract, which is 0.115. That's the probability of you getting a red card that is also a face card. So it's 6 divided by 52. That's what it is. Okay. So what we do then, the probability of getting a red card or a face card is 0.5 plus 0.23 minus 0.115. So that's 0.75 minus 0.115, which is 0.615. 0.615. So you would round that up to 0.62. Okay? The probability of you getting either a red card or a face card in one pull, right? So what we're saying is the probability of me taking these cards and randomly pulling it out and getting a red card or a face card. By the way, this is the ace of diamonds. So the probability of me doing that, of getting a red card or a face card, is 0.62, 62%. That's different, though, than the probability. Let's say, what is the probability of me getting a 4 or a 5. All right, what's the probability of me pulling a 4 or a 5 out of the deck? The probability of me pulling a 4 or a 5 out of the deck. So let's try and erase some of these things. My computer's going to go slow to catch up. What's the probability of getting a 4 or a 5 out of this particular deck? So the probability of getting a 4, there's a 4 of hearts, there's a 4 of spades, there's a 4 of diamonds, there's a 4 of clubs. So the probability of getting a 4 is, there's 4 of those out of 52, 4 divided by 52. That's 0.0769, okay? 0.0769 is the probability of me getting a 4, okay? 0.0769. That is the probability of me getting a 4. The probability of me getting a 5 is also 0.0769. So 0.0769 times 2, right? So it is plus 0.0769, is what I should have said. 0.0769 plus 0.0769 means that the probability of me reaching into the deck and getting either a 4 or a 5 is, I didn't get it, because the probability is a 0.1538. That is a 15.38% chance. The probability is 0.1538. Now, how come I didn't subtract anything? The reason why I didn't subtract anything is because being a 4 or a 5 is mutually exclusive. You cannot be both a 4 and a 5 at the same time. You are either a 4 or you're a 5. You can't be both. It's mutually exclusive. It's not exhaustive, right? Being a 4 or a 5, there could be other things, right? There could be, 6, 7, 8, 9, etc., right? So it's not exhaustive, but it is mutually exclusive. All right, let's move on to the other rule. But to remember, addition rule, that's when you're thinking or. You get this or that, like out of one event, out of one pull of the cards. So let's do some practice. In a standard deck of cards, what's the probability you get a red card or a black card? Well, that's easy, right? The probability of you getting a red card or a black card is 100%. It's 1.0. 1.0. Probability of me getting a red or a black card. Why? Because the probability of me getting a red card is 0.50 plus the probability of me getting a black card, and that probability is 0.50, and 0.50 plus 0.50 is 1.0. And logically, that makes sense. All of these, they're either red or black. So I pull one out, the probability that they're going to be either red or black, 100%. It's 1.00. In a standard deck of cards, what's the probability you get a red card or a face card? We just did this one, right? So a probability of getting a red card or a face card is, so remember, this is what you do. You take the probability of you getting a red card, which is 0.50, plus the probability of you getting a face card, which is 0.23, minus the probability of you getting a red card that is also a face card, and that is 0.115. So the actual answer is 0.615, or 0.62 would be the most correct answer. All right, multiplication rule. When we're doing the multiplication rule, the easiest way to think about this is in two events, right? Like not just pulling the card out once, but pulling a card out and then pulling another card out. Whenever we're doing the multiplication rule, it's the probability of this and then this happening. So this and then this happening. When we're talking about these, we need to think about the probability of the first thing happening and then the probability of the second thing happening if the first thing happened. Does that make sense? So it kind of depends on whether these events are independent or dependent. By independent, you should say, hey, are these totally independent of each other, right? So for example, if I pull a card out of the deck and I put it back in, and then I pull a new card out of the deck, those two events are independent, right? The probability didn't change. So let me give you an example. So what is the probability of me getting a red card and me then getting a red card, and then let's do this mutually exclusive to make this easier to understand. So what's probably me getting a red card and me getting a spade? Okay. So that kind of depends on if these are independent or dependent. It depends on if I put that first card back in or not. So what's the probability of me getting a red card and a spade? So let's do the first one. The probability of me getting a red card is 0.5. All right. Probability of me getting a red card the first time is 0.5. So in this one, this is actually the Queen of Hearts. That's the probability of me getting a red card is 0.5. But then and means I've got another event. The probability of me getting a red card and the probability of me getting a spade. So the second one, I put that Queen of Hearts back in. I put the Queen of Hearts back in the deck. I replaced her. I put her back in. And now I'm going to take out a new card, and it is not a spade, right? But if it was a spade, what would be the probability of that happening? Both. We want the probability of both of these happening. Now, the probability changes depending on whether or not I put the Queen of Hearts. I pull one out. It's the Queen of Hearts. It depends on if I put her back in or if I keep her out and put her somewhere else. Okay? Those probabilities will change. And for this, we do the multiplication rule. So let's think about this. All right. So what is the probability of me pulling out a red card and then pulling out a spade? So the probability of me pulling out, so remember, both of these things have to happen. It's an and. That's why we say and. Pulling out a red card and then pulling out a spade. So in this case, the probability of me getting a red card is A. So the probability of me getting a red card is 0.5. Okay. And then I multiply 0.5 times the probability of me getting a spade. All right. The probability of me getting a spade is the probability of B given A. Well, if I pull out a red card and then I put it back in, then the probability of me getting a spade is 13 divided by 52, which is a 25% chance, 0.25. So if I pull out one card and then put it back in and then pull out another card, then the probability of one of those being a red card and one of those being a spade is 0.5 times 0.25, and that is 0.125. Okay, 0.125. So that is the probability of both of those things happening with replacement. In that case, you remember, I put the queen back in. This changes if I don't put the queen back in anymore. So what is the probability of me getting a red card and then getting a spade if I don't put the queen back in? Well, the probability of getting a red card stays the same. It's still 0.5 on that first round, right? But then the probability of me getting a spade now changes because it's not 13 out of 52 cards anymore. It's now 13 out of 51 cards because I took the Queen of Hearts out of there, right? And so 13 divided by 51 is pretty close still. It's 0.2549, right? So instead of just 0.25, it's 0.2549. And when you multiply those two things, you get 0.12745. when we replaced the queen, we had a lower probability of getting a spade the second time, right? Because when you put the queen back in, the probability of getting a spade is 13 out of 52. But when you keep that queen out, the probability of getting a spade actually increases slightly when you don't replace the queen. This is a probability of this and that happening. It's not me not getting the probability of a red or a spade. It's the probability of getting a red and then a spade. That's how you should think about those two things. That's why it's why a small probability instead of a large one. All right, let's do some questions with this. I get a standard deck of cards. What's the probability you'll get a red card and then a queen with replacement? So what we're trying to do is trying to figure out what is the probability you get a red card and then a queen. So this is the multiplication rule because it's and. A red card, that's 0.5. Okay, so getting the red card, the probability of that happening is, let me try to find a place where I can write this, 0.5. But then I need to multiply that times the probability of getting a queen. Well, in this case, I put the red card back in, right? So there is replacement there. There is replacement there. And the probability of getting a queen, there are 4 queens in the deck. 4 divided by 52. 4 divided by 52, if you remember, is 0.0769, okay? So 0.5 times 0.0769. And that is 0.038. 0.0384. So 0.0384. You round that up to 0.04. So there's about a 4% chance, the probability is 0.0384, that you will pull a red card out the first time, then you put it back in, and you're going to pull out a queen. Probability of that happening is about 0.0384. Next. In a standard deck of cards, what's the probability you get a red card and then a face card, again with replacement? All right, so the probability to get a red card is 0.50 times the probability of getting a face card. The probability of getting a face card is 12 divided by 52. There's 12 face cards in the deck. Okay, so 12 divided by 52 is 0.23. So 0.5 times 0.23 is 0.115. That sounds pretty familiar, doesn't it? Is 0.115. 115. 0.1. Come on, let's see if it'll do it. 0.1154. It's not going to let me do it. I don't know why. 0.115. So the answer would be you round it up to 0.12 if you round it to 2 decimal places. So the probability of that happening is 0.115. All right, which is half of a quarter. Okay, close to half of a quarter. All right, next question. In a standard deck of cards, what's the probability you'll get a red card and then a club without replacement? This is the same as the one we did before. So it is 0.50. That's the probability of you getting a red card times the probability of you getting a club if you don't put the other one back in. So this is 0.50 times 13 divided by 51. Which is 0.2549. And when you get that, you get 0.12745. You round that up to 0.13. Great. I want to know the probability of getting heads or tails in one coin flip. Head or tails in one coin flip. Which probability am I going to use? All right, well, you can use a multiplication rule if you want. The probability of getting heads is well, you can't use a multiplication rule, I'm sorry. A head or tails, so or is going to be the addition rule. Head or tails is, I got 0.5, that's the probability of one thing happening, or the probability of the second thing happening, that's 0.5. 0.5 plus 0.5 is 1. If you flip a coin, you're going to get heads or tails. That's the addition rule that you would use. All right, thanks everybody.